Um, so what I'm going to tell you about today is a little bit different than we started talking about yesterday, where we focused mostly on fluids. I'm going to be talking more about a problem. I'm going to be talking about a problem in solids, crystalline solids per se, and you'll see why crystallinity is an important part. And I'm going to be talking about grain boundaries and how they move. I'm going to start with a microscopic description of how grain boundaries move. And then, but the overall goal by the end is what I'm going to try to do is take that microscopic description and try to propose a macroscopic model based on this microscopic description. So you'll have to bear with me in the beginning while I do some of the microscopics, and I have to do that so we can get to the macroscopic part. Like most problems, when you get to be a senior professor, that means that most of the work is done by younger people. So all the people in red here, Lu Chan, who's around here someplace, was a graduate student of Yang Xiang, and she spent 6 months with me at Penn, and some interesting things came out. Yang's a longtime collaborator of mine. Chao Zhen Wei is a postdoc at University of Science Technology. Jian Han is probably the person most responsible for the work here, and he just defended his PhD a few weeks ago. And these are two other students, and the ones in black are written because those are the professors, and that's all we know. As we all know, professors just talk to the students who actually do the work. So let's get on with it. So let me try to sort of tell you first, what are we talking about here? So what you see are two kinds of domain structures. This is a polycrystal. This is a ceramic material, calcium carbonate. This is a soap froth, bubbles. This is the head of a beer. This is dishwater, right? And the interesting thing about them is if you look at it topologically, the structures are very similar. You have domains surrounded by walls. The walls are delimited by junctions like this or like that, and those junctions meet at points like this. And it's very similar, but in fact, they're actually quite different, and I'll tell you about what the differences are in a minute. But in most cases, the way people talk about the evolution of these structures is by saying that the velocity of a domain wall, in both cases, goes proportional to the mean curvature at some constant which depends on details. And so you can see that both of these evolution of both of these structures is basically mean curvature flow. And since it's mean curvature flow, we're all very happy because in mathematics we know a lot about mean curvature flow. Okay? So what I'll show you is mean curvature flow is actually just a model for this. It does some things right, but it's pretty incomplete, and I'll try to make the point of why that is. So in the case of a soap froth like this, the domains, the interior is a gas. In a polycrystalline material, the inside of each of these domains is a crystal made up of atoms in a regular lattice. The walls between grains or between domains here are liquid films. Here, there are the defects we call grain boundaries. Grain boundary is where the crystal orientation changes discretely. Okay? So both grains have exactly the same crystal structure. They're just different orientations in space. And again, the grain boundary is just where you have a discontinuity in the orientation of the lattice. And then when these domain walls move, or basically in the soap froth case, you have gas diffusing through this liquid layer here, these liquid films, and so the kinetics are controlled by the rate of that diffusion. In a polycrystalline material like this, atoms have to jump across and detach from one crystal and attach to the other crystal. And the kinetics, the absolute rate at which this happens, is what determines how things move. Okay, and so since we know a lot about this problem, and it's just mean curvature flow, and if you look at the junctions along which three grain boundaries meet, if the material is isotropic, then these domain walls meet at an angle of 2 pi over 3. And so if I take that as a boundary condition, I can just do front tracking to watch the evolution of these structures. Yeah. Yeah, so the assumption here is that things are moving slow enough that the dynamical effects are relatively minor. But it doesn't always have to be the case. I mean, I can generalize, but I'm trying to give you the classic textbook version. As we always tell students when we tell them, you know, what's in the textbooks, I always tell them that I'm going to lie to you. And I'm going to lie to you every day because you can't handle the truth yet. So I'm taking that point of view here. Okay, so these are just the evolution of structures in two dimensions and 3 dimensions. And I just show this as a cube where it's periodic boundary conditions. Here it's periodic. The thing to note in both cases is big grains tend to grow, small grains tend to shrink. So the total amount of grain boundary area in the system goes down, and that's what drives the system. Okay, it's the reduction in the grain boundary area. And in 2 dimensions, you have a nice thing that grains with smaller than 6 sides tend to shrink, with more than 6 sides tend to grow. Von Neumann told us that quite a few years ago. And it's a little bit more complicated in 3 dimensions. So the rate of change of the area of a single grain, according to von Neumann and generalized by Bill Mullins, is just that there's some kinetic coefficient here, and it just goes like the number of sides minus 6, which is a beautiful result because A, it's exact, and B, it's purely topological. Exact relations are very rare in material science. How many points do I need? So I'm only tracking here, and typically in these we have something like 10 points along a grain boundary. We try to coarsen the mesh as we go. I can give you the reference, but there's lots of ways of doing this. This is actually still pretty efficient. But we use some clever ideas that have to do with the fact that I know a little bit about the mathematics here. So this nice result from 1950 was really perfectly topological. The question was, how does it work in 3 dimensions? So I did a little bit of work with Bob McPherson at Princeton at the Institute for Advanced Study. And we basically solved the problem in all dimensions and showed that the von Neumann result is 2 dimensions. Is a special case. One of the amusing things is McPherson actually has von Neumann's old office at the Institute. So it was sort of natural we did this together. And what I'm showing you here are just 2 grains plucked from the interior of that one, because what I want to do is make the following point. Those relationships that I just showed you about how the area or the volume of each grain evolves works perfectly well until you get a change in topology. And as you can see, topological changes happen all the time. So that's a really important thing, is you've got to be able to describe the topology part of this. And you could sit here and watch this all day. Okay. Now, having told you how curvature flow works and how the classical model works, next thing I'm going to tell you is that's very nice, but what really happens now? So that's really what we're going to discuss. And so if I look at a polycrystal, surprisingly, materials are actually made of atoms. And because they're made of atoms and there's certain orientation relationships, there's by necessity a certain kind of anisotropy that happens in these models associated with the fact that these crystals have particular symmetries. They don't have like the bubble problem where the only symmetry element is the identity element, right? These have real symmetries and they're important. And in fact, to describe a grain boundary, I need 5 degrees of freedom. So if I take 3 axes of a crystal here, 3 axes of a crystal here, if I keep this fixed and I rotate the other, there's 3 degrees of freedom. And then once I fix the relative orientation of the 2 crystals, there's a boundary plane, and the boundary plane has a normal, which has 2 components. So there's 5 degrees of freedom for a grain boundary. And so you would expect that then the properties of grain boundaries are in a 5-dimensional space. And the point is, you can't possibly get mean curvature flow, which knows nothing about these degrees of freedom, the crystal structure, the crystal symmetries. And so what I'm going to try to do is be sensitive to that, and then we'll go back to those macroscopic equations. And to start, I'm going to talk just very briefly about what happens on a free surface. So if I have a free surface like this, and I add atoms from the gas, they can come down, they can land on these terraces, and they can move back and forth, and they can attach to steps. So the way the surface moves up this way is by attaching atoms to the steps, and the steps move laterally. So it's the lateral motion of the steps which gives you the normal motion of the interface or the surface. Okay, so normal motion of the surface is the lateral motion of the steps. Okay, but the crystallography is going to tell me which kinds of step heights are permissible. I can have a 1 atomic plane high or 2 atomic plane high or something like that. So there's a discrete set of step heights that crystallography tells me. And here, the rate at which these steps move depend on what's being attached to those steps. Okay? Now, let's go back to grain boundaries. In grain boundaries, we have the same sort of thing where these are 2 crystals. I just put these atoms white, these atoms black. It doesn't matter. I'm just coloring them so you can tell which one's which. And you can see they have the same crystal structure, and they're misoriented, this arrangement relative to this one. And there's a very fine lattice that we can describe for the 2 crystals together. It's called a DSC lattice. It's a detail. I'm not going to talk about it today because it'll take me another half an hour. But the point is, the way a grain boundary moves this way is by having a step in the boundary, and the propagation of the step that way translates the grain boundary that way, just like at the surface. But now, on one side, I have a crystal, just like in the surface case. On the other side, I have another crystal. And when I put those 2 things together and try to match them across this grain boundary plane, you can see that very often what you have is a different number of lattice planes this way than this way. So here I have an extra plane. And so this is the classic picture of a dislocation. Okay? And in fact, there's the dislocation. And for those of you who've done dislocation theory before, if you integrate the gradient of the displacement field around a loop that encloses a dislocation, you get a vector, which is called the Burgers vector. That's the closure failure. And that Burgers vector characterizes this dislocation. And because I have an extra plane of atoms here, this thing has a long-range elastic field. So the point is, in grain boundaries, not only do I have steps to worry about, but I also have dislocations to worry about. And those 2 things together, this defect, which has both step character and dislocation character, is called a disconnection. Okay? It's a line defect that lies along the grain boundary, just like steps lie along the surface. The steps can't move into the crystal or into the gas, so too disconnections are constrained to lie on the grain boundary. Okay, we're good? Okay. So this object here, this disconnection, is characterized both by the Burgers vector and the step height. And just some quick atomistic simulations. So this is the magnitude of the Burgers vector, the first number here, and the step height is in these numbers here. What I want to point out to you is just like in the surface, I can have steps of size 1 atomic spacing or 2 or 3 atomic spacings. So too, disconnections can have steps of different height. So this is 3 halves, and that's 4 in some units. But the point is the Burgers vector is the same. And if I look at the elastic stress field around them, the stress field, even though they have different heights, since they have the same Burgers vector, the stress fields are identical. So the stresses are controlled by the Burgers vector, the dislocation character, and the steps don't really affect that. And the interesting thing is this is a special case, we call it a pure step, where you have a step and the total Burgers vector happens to be 0. But it doesn't have to be. And you can see here there's no long-range elastic field associated with that. Okay? So the point is the Burgers vector and the step height are 2 characteristics we can talk about. So let me just summarize where we are right now, and then I'll move on. So grain boundaries move by the formation and motion of disconnections. So here's a disconnection, which you see is 2 steps. If those steps separate, and since they have a Burgers vector, first if they separate, the grain boundary moves down to here. But since there's a Burgers vector, there's a shear associated with it, when these things move out, the crystal is sheared over. So you get a coupling between motion of the grain boundary this way and shear of the 2 crystals laterally. Those 2 things are necessarily coupled. Okay. So the point is, just like we saw that there's a lot of possible step heights, 1 atomic plane, 2 atomic planes, 3 atomic planes, there's also a set of different Burgers vectors. The nice thing is crystallography tells us exactly what it is. Again, I could talk about all the crystallography with you and tell you how to find out what they are, but you could take this, I'll just assert it right now. The disconnections are confined to the interface, and the Burgers vector and step height are conserved quantities. Okay. So this is the picture I just...
Say you have a step 1 atomic thickness. You can sometimes double that.
Yes.
What's your forward of that?
Yeah, so that's right. The step heights, there's many possibilities. So I can combine 2 steps of, say, step height 1 to make a step of step height 2. But I'm still conserving.
No, what I mean is, say everything's nucleating here.
Yes.
You have 1 step coming in here.
Yeah.
And the second step starts out.
Yes.
Catches up with the first one.
Yes.
So H is now twice.
Yes. Right. So the total step height is conserved.
Okay.
Yes.
Not local.
Right. I mean, there's summation rules. You know, if I add 1 to the other, it's got to be the sum of the 2 or the difference of the 2. Okay. So this is the point I'm showing you here. So here's the Burgers vectors here and here. I put in a shear. The shear couples to the Burgers vector, makes these things move sideways. When they move sideways, the grain boundary goes down by 1 step height and shears over by 1 Burgers vector. Okay? And the ratio of the velocity of the 2 crystals relative to each other tangentially and the rate at which it migrates this way is just given by the ratio of the Burgers vector to the step height. Okay? We're good? Okay. And that's called the coupling factor. It's the ratio of the Burgers vector to the step height. Now, all this is nice. Does it really work? So there's a simulation done by Yuri Mishin and his student. So what we have here is a crystal of a bicrystal. You're shearing the top with respect to the bottom at fixed velocity. The red line is a fiducial mark, which means I just colored a line of atoms red. They have no difference in property. Experimentally, it's usually a scratch. It's fixed to material points. So what you see is here's the grain boundary, and you can see as I'm shearing the top relative to the bottom, the grain boundary is moving down, and the crystals are shearing relative to each other. And the slope of this line here is related to beta. Okay, so if I measure that slope, I know what beta is. Okay, so theory, simulation, does it really work in real materials? So what I'm going to show you now is a movie done in transmission electron microscopy of a thin film of ultra fine grained aluminum, and it's at 420 degrees, and they apply a stress this way. Here's one grain boundary, another one, another one. This is the top surface of the bottom surface of the thin film. That's the top surface. Now, you can see the grain boundary is migrating, but as the boundary is migrating down, you can see all these defects moving laterally along the grain boundary. Those are the disconnections. Let's see, is it still moving? Yeah, it's still moving. It's beautiful to see them in action. Okay. Oh, by the way, this other stuff here, that's just dirt on the surface. Okay. So that's the crystallography, or the structure part. And that's the connection between the stresses and the motion. But let's talk a little bit more about the thermodynamics. So if I nucleate a pair of disconnections here, they have Berger's vectors and step height. So the total energy to form this is the step energy. That's how much it costs to create those steps. And that's proportional to like a surface energy times a step height. There's a core energy, because right around here, the bonding, like the core of a dislocation, is very nonlinear. So it's just proportional to the number of disconnections per unit length. And that's an elastic constant, and B is the Berger's vector. And the important thing is those two steps, since they have elastic, those two disconnections, since they have elastic fields, have elastic interactions, one with respect to the other. And those are like dislocations, and like all dislocations, the interaction energy goes like the logarithm of the separation between them. Okay, that's the energy. Now, if I apply a stress, tau, that stress couples to the Berger's vector, because the Berger's vectors represent a strain, and the stress and those strains are conjugate to each other. So now if I look at the energy as a function of stress as I separate the two disconnections, this part here goes up like that. This is the mechanical work term, this one you're adding. It's linear in separation, delta. If I add it together, I get a barrier. And that's the nucleation barrier for the disconnections. And I can change that barrier dramatically just by changing the stress. Okay? On the other hand, if imagine I have two grains, I'll draw a simple picture. If I say this one has an energy per unit volume psi 1, or say energy per atom psi 2, if there's a jump in between this, we'll say psi is equal to psi 2 minus psi 1. So that's basically the jump in the chemical potential across a grain boundary. And I can add that by various ways, but the point is, as the grain boundary moves, I'm converting some of material 2 into material 1. Since they have different energies or different chemical potentials, then I get a contribution of the energy which is proportional to the step height and how far the steps have moved. Okay? So again, you get the same sort of curve here, except the work is being done by the jump in chemical potential psi, And you get the same sort of picture in both cases. But note the chemical potential couples to the step height. The stress couples to the Berger's vector. So depending on how I drive the motion, in some cases it's the step height that matters, in some cases it's the Berger's vector that matters. But since they have to move together, the step height and the Berger's vector, one gets dragged along with the other. So even I can apply no stress and only apply a chemical potential jump, but the Berger's vector has to move along with the step. Okay? I know I'm going fast. I talk fast, sorry. And now, as I told you, there's a spectrum of possible Berger's vectors and a spectrum of possible step heights. And so if I look at all the possibilities that crystallography allows for 3 different grain boundaries, is I get energies for nucleation of those different disconnections as I change B and H. If I look at all the possible B's, all the possible H's, so for one particular grain boundary, this is the spectrum. For another grain boundary, that's the spectrum. Another one, that's the spectrum. And I can write it all down. Now, I can do trivial statistical mechanics here. And I say, well, what's the probability I nucleate a step disconnection where it's got a Berger's vector characterized by I and a step height characterized by J? Well, it just depends on the nucleation barrier, e to the minus that barrier over KT. There's the barrier. Okay? So I can figure out what's the probability density of each kind of disconnection. Okay? At low temperature, I'm just going to get the lowest energy one. At high temperature, I may have many. Okay, so that brings me to a very nice little set of simulations my student Spencer did. So this is like the simulation you saw before, where what we do is we have a bicrystal. The bicrystal has certain chemical potential in this side and that side, so there's a jump in chemical potential. The jump in chemical potential, if this one's higher than that one, the boundary wants to move up. But since there's a Berger's vector, it's also going to shear. Okay? And if you look at this in the simulation, so again, we put it in fiducial marks here. Here's the grain boundary. It's periodic this way. So you can see that as the grain boundary moves up, this line, as the grain boundary moves up, it's also shearing this way, so we get a finite slope. That's the ratio of the Berger's vector to the step height. Well, it's 1 over that. And it turns out in this case, it's the lowest energy disconnection that works. Okay, very nice. I haven't learned anything because this is just like the con mission simulations I showed you a minute ago. So what we're going to do now is exactly the same thing, except instead of letting the top and bottom of the 2 crystals be free, I'm going to fix the ends. So now as the grain boundary moves up and it wants to shear, since the ends are fixed, it's got to strain in order to fit in those fixed end conditions. So as the boundary moves up, I'm building a strain or a stress. And as I build that stress, obviously the energy of the system is going up. And eventually that energy can become so high that I counteract this chemical potential difference. And it's got to stop. And so this is, again, the same kind of simulation with fixed ends. And you can see the grain boundary moves up. But then if I wait a really long time, it stops moving. And if I look at the position versus time, it moves up, wiggles around a little bit, but goes to a constant value. And the interesting thing is the boundary is migrating this way. The stress is building because the farther it moves, the larger the shear strain. So I'm building that, and eventually these 2 things balance. And I can tell you exactly how far it needs to go until those energies balance exactly. And so these lines here are just analytical predictions. Okay, now this is the fun one. Now what we're doing is exactly the same thing, is we're fixing the ends, and I'm picking a different grain boundary in this case. And what you see is when I try to drive it up by the difference in chemical potential, I get the normal shear coupling. I get that slope there related to beta. But at some point, as it's going up, it's shearing. But at some point, it continues to go up. It starts to shear the other way, and then shear the other way, and shear the other way. So what nature is actually doing here is it's saying, I want to migrate up. But as I migrate up with this fixed beta, Berger's vector and step height, I'm building the shear stress. But at some point, that gets turned off because the stresses get too high. But now I can nucleate another disconnection that has the opposite sign Berger's vector. And now, instead of as it moves up and shearing like this, it shifts and unshears. And then shears back, unshears, shears back, unshears. And so if I watch, sorry, I lost my pointer. So if I look at the position, the boundary is moving up at a more or less a constant rate till it gets to the end. But the stress is going down, up, down, up, down, up, each corresponding to a different slope there. Okay? So this is how nature outsmarts the simple thermodynamics based on one disconnection by saying, well, if it gets too hard to move one kind of disconnection, just move the other one. Okay? Now, which ones actually work? So I have a statistical distribution of different kinds of Berger's vectors, different kinds of step heights. I'm not going to bore you with going through the details, but the point I want to make is if I look at the average Berger's vector, the rate of change, and the average step height, the average distance it's traveled. So this is the average distance it's sheared. You find out that you have a little matrix here that couples the rate at which it shears to both the chemical potential difference and to the stress. And how far it moves is coupled again to the chemical potential difference and the stress. But now we go back and say, well, Onsager told us something else about this system. And that is to say, if you have a matrix that's of kinetic coefficients in this linear response regime, these two things have to be equal. So the off-diagonal terms have to be equal. And in fact, you can just compare them, and they are exactly equal. I didn't expect that, but in retrospect, I should have guessed. Okay. 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 Now we have a microscopic model. Let's start building a macroscopic model from this. So really what I want in a model is something, I don't want to track every disconnection on every grain boundary along each grain boundary and then repeat it for all grain boundary in the system. It's too much work. I want an equation of motion for the boundary. I want to increase, I want to go down, I want to decrease the dimensionality of my problem. So what I want to do is try to come up with a way of describing this that it just doesn't describe bicrystals, which I like to refer to as tame grain boundaries, because it's just isolated, domesticated grain boundaries. In a polycrystal, the real case, these are grain boundaries in the wild, where you have all possible orientations, junctions between them. We want something that we can use for a case like that. Okay. So, and we want to respect the fact that this moves by this disconnection mechanism. We want to be able to talk about all kinds of driving forces, work for bicrystals and polycrystals, and we want it to be computationally tractable. So that's the goal. So let's do this. So we're going to try to sort of homogenize this in the following way. So if a microscopic view is I have all these steps here. This is, by the way, the same way people do equations of motions for surfaces. So I have the steps here. And if I know what the density of steps are, then I know the slope. So the step height times the density is just the first derivative of the height profile. Okay? So that's the first step. And if we just do conservation, so this is just pure kinematics. So if I look at the rate at which the height evolves, as the derivative of h with respect to time, is just the velocity of the disconnections times the density of disconnections, which is the slope. And then what I'm going to do, and this is an assumption, is I'm going to say then that the velocity of the disconnections are just proportional to the total force on them, which I can get by the variation of the free energy with respect to displacements of the steps, times a mobility. That's an assumption. Okay? I mean, it's linear response, so it's a good place to start. Okay? And the mobility here depends on all the details of the atomistic structure of the disconnections. And this force depends on the chemical potential difference. It's going to depend on the applied stress. It's going to depend on, as I'll show you, the curvature. So if I actually write it down, and here's all the basic pieces. So this part is just the mobility times the density times the force. So this force actually has three parts to it. The first part is the interaction of the Burger's vector of the disconnection with the stress. The stress has two pieces. There's an applied stress, which I call tau, and there's the fact that each disconnection interacts elastically with every other disconnection. So I've got to integrate out over all the elasticity. So this is basically just a Green's function here. So that tells you the stress related to the density of disconnections here. And this K here is just an elastic constant. Okay? Computationally, this part's work. Okay? These two terms here both couple the motion of the disconnection to the step height here. This one is due to the chemical potential difference. This term here is basically the mean curvature term. And basically, in a discrete picture, the way I can get a mean curvature term is I just imagine that the steps along the grain boundaries are randomly walking. When they happen to hit, they annihilate. And if you do a little bit of work, you can show that that's going to give you something like this. So this goes back to, this is the only part that's in the mean curvature flow model. Okay, one more piece, and then we're ready to go. So this was the conservation law we had before, that this is the rate of change of the step height of the height of the height profile. This is the velocity of disconnections. That's the density of disconnections. Before we said it's 0. But if it were 0 on the right-hand side, if it were 0 on the right-hand side, that means that if the slope is initially 0, it'll always stay 0. So I have to add a source term. Where do disconnections come from to begin with? So I'm going to postulate that there must be a source term there. And what I'm going to do is say, well, that source term is just related to the equilibrium concentration, thermal equilibrium concentration of disconnections in the system. Okay? So I can do this just like, this looks like semiconductor physics, but it's, so this is just the concentration of plus steps, plus disconnections, times minus disconnections. This is the formation energy of the dipole. And so it looks like that. And so this is just an assumption here. It's the simplest assumption. I'm going to assume that the density is in equilibrium. So if I take this thing, I can relate it to my source term G. I have this relation here, because this is the force term, which it affects the barrier. And at the end of the day, this is my equation of motion. B is now comes from this source term. So if I had a classic problem where I just had mean curvature flow, I'd have this term, this would be non-zero, this and this would be 0. I would have this, and I need another constant in front, which has to do with nucleation. So all the temperature dependence in this problem is in the mobility of the individual disconnections, the source term, and possibly which B and H gets selected at that temperature. Okay, so that's my equation of motion. It's a little bit more complicated than mean curvature flow, but it's got microscopic details. I can build in all the crystallography. So let's see, how does it work? Okay, so that's just repeated. So if I put the source term to 0 and I start with a little perturbation on a grain boundary, the interesting thing is, first, it's going to get flatter and flatter because there's no stress, there's no chemical potential difference. So surface tension just drives it flat. The interesting thing is if I don't put on, if I do it at t equals 0, I get these little corners in here. But if I go to finite temperature, those corners all go away. Okay? Second thing, now if I do this at finite temperature, so I'm starting with a flat grain boundary here. I'm going to pin it at two ends. I'm going to apply a stress. And the grain boundary is going to move like shown in the blue curve here. And then eventually it's going to go to some steady state shape. If I do the same thing at a different temperature, of course, equilibrium doesn't care about the kinetics, so it goes to the same final shape, but the evolution of the profile is different. And that's because the constants MD and B are all different in this case. Okay, let me do one more problem as an example. Let's go back to grain boundaries in the wild. So here's a polycrystal, a bad polycrystal, by the way. It's not a very good description, but there's triple junctions here where three grain boundaries meet. Now, if I nucleate disconnections here, they're going to migrate until they get to the triple junctions. They're going to start to pile up there. They can actually go through the triple junctions, but that's another story we don't have time for today. But as you nucleate them, they're going to pile up and you get some non-uniform distribution of disconnections along the grain boundary. And again, it's driven by an applied stress, so it couples to the Burgers vector. But since I'm piling up Burgers vector, and those Burgers vectors have a step height associated with them as well, when I pile up the Burgers vector, I'm also changing the shape of the boundary. And so if I know the distribution of disconnections, I know the shape. So that's the distribution of disconnection. I can actually solve it analytically. It's a classic dislocation theory problem. Now if I then put in the Burgers vector, if I put in the step heights and the relationship between them, that's the equation here. That's the shape that I should get. So now we go back to an atomistic molecular dynamics simulation. So here's a grain boundary. Here, two more here, triple junctions. You apply a shear stress like that. And we're going to draw in two lines. Again, these are scratches. These are fiducial lines. Okay, I apply the shear. And this is actually the simulation results. And you can see this line here. So these are the grain boundaries afterwards. That's the final profile. This is where this grain boundary was initially. You can see the lattice is sheared like that. And that's the final profile. And that's the prediction of what it looks like. And if I plug in which Burgers vectors and step heights are allowed for this grain boundary, this has no adjustable parameters. Okay, Okay, I got 30 seconds to talk about triple junctions. As the disconnections flow into the triple junctions, I have to have some flux balance. You can do it. And actually, one thing that comes out of it is naturally triple junction drag, which means that the angle actually starts to deviate from the equilibrium angle if you assume that the reaction of the disconnections at the triple junction has a kinetic barrier. And so if you do that, you can find the angle. You can find how the angle in this steady state dynamical problem depends on the kinetic coefficients. And so triple junction drag and deviations of the angle from the equilibrium angle in this dynamic problem, it just comes out. No work. Okay. Da-da-da-da-da. Oop. And those are the conclusions. You could read them yourself. Thank you for your attention. Pretty close.
Question.
Eugene.
We know that the dislocation core energy is pretty high. So my question is, what is the physical amplitude of all those Boltzmann exponential in physical terms?
Yeah. So first, keep in mind that the Burgers vectors are quite small. And so if you go back and you go to a very simple boundary like a sigma 5 boundary, I'm using a language that Eugene knows. I don't think most of the other people know it. But if you go to a very simple boundary like sigma 5, you find out that those energy levels are fairly close together. So at about half the melting point, you only see the lowest energy one. So the Boltzmann factor will only pick out the lowest one. As you go up to about 3/4 of the melting point, then you start activating the second one. So in that simple boundary, that's about where it is. So that's about the ratio. That's where those two things those Boltzmann factors are similar. Okay. By the way, but it's very sensitive because, so if I look at the roughening of a grain boundary, some grain boundaries roughen at a low temperature, some never roughen, and the crystal melts first. It just depends on the difference in energy between the different disconnection states. Okay, so different grain boundaries can be very different in that respect. By the way, some grain boundaries slide. That means you're activating multiple modes. Some don't, which basically means that you're only getting the lowest one.
When you showed these nice oscillations of the first one, the two examples were was it the position of the grain boundary or was it the shear stress that oscillates?
So in the case where it's oscillating, the position sort of wiggles around but keeps going up. The stress goes up, down, as you nucleate the different ones.
But it happened actually both examples, except in one it dies down, right? So it's the same mechanism?
Yeah, so in one grain boundary, it's very difficult to nucleate the second kind of disconnection. So in that case, it shears, and then once the shear stress gets too big, the process turns off. The other one, as you build that shear stress, and since there's another disconnection, the other type available, it'll start shearing the other way. So it's just the difference in what the difference is between those two different grain boundaries. It goes back to the question Eugene asked, which is what's the likelihood of activating the next mode? And that's very sensitive to which grain boundary it is.
First one, I did not understand when you showed the experimental video, you said the simulation does not work. I did not get why.
Oh, no. The simulation works. What I say what doesn't work is if I was going to use the classical equation of motion where it just says velocity proportional to curvature, that doesn't work there because in that case, in that movie, what they do is they take the sample, they anneal it until nothing's moving anymore. Then they apply stress and it starts to move those disconnections. So it's the stress coupling, not the curvature. term that's driving it. But yeah, this version works. Yeah.
Second question. So in your simulation, you have this stress and stress, this periodic feature.
Yes.
Do people observe experimentally that there are such periodic features?
No, and it's for the following reason. What we're doing is we're doing a very narrow simulation cell. So you're only nucleating one pair of disconnections at a time. In a macroscopic sample, you're nucleating all over the place. And so instead of going up, down, up, down, up, down, you're averaging over all of that. And the average stress just goes to a low constant value. And you just see you'll see just a smooth growth of the stress and then become a constant value. And so you're not seeing shear, shear, shear like this because you're averaging over many and depends on where they get nucleated and when they get nucleated. So we actually picked a very narrow simulation cell so we can count every one that nucleates. But yeah, that's a good point.